Here's a common task in a chemical lab. We want to run a chemical reaction, and we have figured out how many moles of the chemical we require to get the job done. So using our lab equipment, we now need to measure out the required moles of the chemical. Now, how we accomplish this task depends on the phase of the chemical we have at hand and our ability to do the computation. Converting moles of the chemical to mass or volume quantities that can be easily measured with our lab equipment and glassware. In other lectures, we've learned how to do this kind of computation for pure solids, pure gases, gas mixtures, and pure liquids. What we haven't covered is how to do the computations and experimentally manipulate solution mixtures. So we need a certain number of moles of a chemical to do a reaction in our lab. Now, if the chemical we need is solid, we use the atomic or molar mass of the chemical to convert the moles required to the mass of chemical and use the appropriate balance, a top load or analytical balance, to weigh the chemical. Done. Now, if the chemicals we need are gases, we can measure the temperature in the room and the volume of the vessel we plan on using to contain the reaction. We then use a gas equation of states such as PV equals nRT to calculate the pressure or partial pressure of the chemical required to get the needed number of moles in and deliver the gas to the reaction vessel until we reach that pressure. If the vessel is made of a flexible material like a balloon, we measure the atmospheric pressure and the temperature in the room, and then use the equation of state to get the required volume of the chemical and put material into the balloon till it blows up to the right size. Done. Now, if the chemical is a pure liquid, we take the moles we need of the chemical and convert to a mass using the atomic or molar mass. We could use a balance to weigh the chemical, or with a bit more effort on our part, we can measure out a volume of the material. We now know that it is a rather straightforward computation to use the density of the chemical, our mass-volume connector, to calculate the volume of material we need if we know the mass. Chemists have a variety of different types of glassware to measure volumes. Beakers, graduated cylinders, volumetric flasks, pipettes, burettes, and syringes. Which piece of glassware you use, like all measurements, depends on the size of the quantity you want to measure and the precision essential to get the job done right. So we can just measure the correct volume of chemical required. Done. But many chemicals are not sitting on our lab shelves in the forms we just mentioned. Many times the chemical we need is part of a liquid mixture. That requires additional information and a different computation to measure out the required number of moles of the chemical we so desperately need. What we require is the concentration of the chemical in the liquid mixture. We call liquid mixtures solutions. There are heterogeneous mixtures called immiscible liquids, such as oil and water mixtures, and homogeneous mixtures called miscible liquids. For miscible liquids, there is usually a dominant component that has a higher concentration than the others in the solution. This component is called the solvent, and the lower concentration components we call solutes. For miscible liquids, there is a famous saying that states, like dissolves like. If the solvent compound is a polar molecule, it will have an affinity for other polar molecules or ions and will tend to dissolve them. Water and ethanol are both polar and very miscible. It follows that nonpolar molecules will tend to form miscible liquids with other nonpolar or weakly polar compounds. Also, we know that salts dissolve well in polar solvents like water, but not so well in non-polar solvents. For example, sodium chloride solid, NaCl, is almost completely insoluble in the non-polar liquid tetrachloromethane, CCl4. There are many ways to characterize the concentrations of the different components in a solution mixture. One of the most important measurements of concentrations we'll use in chemistry is called the molarity. The value of molarity is found by taking the moles of a component in the mixture and dividing by the total liters of the solution. The unit of molarity is the capital letter M, and it's typical to say molar when describing the unit. Another way to think about this value is that for 1 liter of the solution, the molarity will be how many moles of the component are present. So let's say we have a 0.10 molar solution of sodium chloride in water. This mixture can be described as an aqueous solution of sodium chloride. We now know that 1 liter of this solution will have 0.10 moles of sodium chloride dissolved in it. Now, we can do a variety of different computations using this new quantity. If I have 8.9 milliliters of a 0.20 molar aqueous solution of calcium chloride, how many moles of calcium chloride do I have? We now know that 0.20 moles of calcium chloride are present in every liter of this solution. We'll first convert our milliliters of solution into liters and then set up the molarity relationship in a way that divides out the liters and gives us 1.8 times 10 to the minus third moles of calcium chloride. Let's do another one, okay? Now, if I need 0.467 moles of sugar for a reaction, and all I have is a 2.50 molar aqueous solution of sugar, how many milliliters of this solution do I need to dispense to be assured that I have enough sugar for my reaction? In our solution map, we have moles, and we need to get to milliliters of solution. We first convert the moles to liters by way of the molarity, which is 2.50 moles per liter of solution. Notice that we divide the moles of sugar by the molarity of the solution, canceling the moles. The last step is just converting the liters to milliliters, obtaining a final answer of 187 milliliters of solution. Now, what would be the molarity of a solution if I dissolve 20.0 grams of sodium chloride in enough water to make 500 mils total of the solution? We need to go from grams of our sodium chloride to moles of sodium chloride via the molar mass, giving us moles of sodium chloride solute. We then divide by the total volume of the solution, 500 mils, and finally convert that value to liters of solution, because molarity units are moles per liter, giving us a final concentration of 0.684 molar sodium chloride. So there you have it. If we require a certain number of moles of some chemical in our lab, and the chemical exists in a solution with known molarity, we can easily calculate the volume of the solution that guarantees we've measured the correct moles of the needed compound. Now, though molarities are a common method to measure concentrations, there are other ways to quantify solutes in solutions, and we'll pick that up in the next lecture of this series. Catch you later.